So as requested, I'm just going to do a quick few examples for each of the chapters in, not each of the chapters, each of the sections of chapter 10, which is numerical methods. So the first one is locating roots. This comes from the textbook and it's a 12-mark question that we'll just go through bit by bit. So the first part is show that there is a root in this particular interval. So remember, if there's a root in the interval minus 0.9, minus 0.8, simply if we just substitute that in, we should be able to find that there is a sign difference. So that's the first thing I'm going to do here. So on my calculator, what I'm going to do is just basically code for this. I'm going to put in minus 0.9 first, just because it's this smaller number. And then I'll put in minus 0.8 just afterwards. So that's my first one set up. Then I'm just going to put ants to the 4, minus 21 ants, minus 18. And that'll just basically substitute that in. So that's f of minus 0.9. So if I just put that in, f of minus 0.9, let's just put part A, is equal to 1.5561. So we can see that's positive. And then if I just put in minus 0.8, so clear that off, minus 0.8, save that's my answer, and now put that in. You can see that that's a negative, so minus 0.7904. And that's f of minus 0.8. So that because there's a sign change, there must be at least one root in there. And it says show that there is a root. Well, I can't say there's one root, but I know there's at least one root in that interval there. So sign change implies roots, technically at least one root. Part B, find the coordinates of any stationary points on that graph. So in that case, I want to differentiate, and remember a stationary point occurs when the gradient is 0. So I just want to basically set f dash of x equal to 0. Not really part of this chapter, but it's just getting to think about that. So putting that in here, I know that f dash of x is equal to x. It's going to be 4x cubed. Apologies, let's just change that. Minus 21. And then setting that equal to 0 just to solve. So I'm going to take 21 across, divide by 4. So I get x cubed equals 21 over 4. And then simply just cube root in that one. So x is equal to the cube root of 21 over 4. Cube root, there we go. So that is 1.738 something. Let's just put dot, dot, dot. That's the one of the station points. Appears, yeah, it must have any others here. So we've just basically got that singular station point itself. It does say find the coordinates. So now I need to put that back into my original equation to find my y value. So I could say at x equals this. And then let's just do f dash or f of 1.738 underneath, and that'll tell me my y. So if I take that and put it back into here, I get minus 45.3737 dot dot dot. So this is my coordinate there. So just rounding that off, it's going to be 1.74 and minus 45.37, let's say, to 2 dp. Another way that I will mention about solving that, you could of course code your calculator. So you can say, okay, I want to differentiate x to the 4 minus 21x minus 18. So that's basically getting it to differentiate it. I don't know where it is, so I want to find out when is this x. So I want it to solve for that in a second. I want to know when this equals 0. So I'm just going to put here equals 0 and then go shift solve. If I just press equals, it doesn't matter what you put in here really. Press equals and it should tell me, yeah, 1.73801. And that's using a numerical method via the calculator to actually find this x value. So I didn't even solve that, but I can check that that's right. I can take that value and put it into here and it will do the same thing. So 2 different ways of doing that. Part C, I'm going to try and squeeze just down here. So just in this section, we know that f of x is equal to x to the 4, blah, blah, blah. So we know also that f of x is equal to x minus 3. And then it says x cubed plus ax squared plus bx plus c. So using this, we can hopefully see that this expands to be x to the 4. And then thinking about the terms that are going to give me x cubes, it's going to be this ax squared times by x. That's going to give me a positive a. And then this minus 3 times x cubed. So I get a minus 3 x cubed. Thinking about x squared terms, it's when I times this minus 3 by ax squared. So that's going to be a minus 3a. And when I times x by b, so that's going to be a plus b minus 3a. X squared, and I'm just going to do the same thing for each for bx as well. So minus 3 times bx will give me a minus 3bx, and the other way to get an x is by timesing x by c. So it's going to be a plus c minus 3a, nope, 3b, sorry, x, and finally we've got a minus 3c. Using the fact that we know that there's no x cubes, there's no x squareds, we can try and find these out. So I know that x cubed is 0, so a must be 3. I know that x squared is 0, so putting that in here, I know that b must be 9. And finally, for the c term, I know that that the constant is minus 18. So 3c is 18, so I know that c is 6. So just a quick compare coefficients there to get that last little bit. Finally, part D is to try and sketch this graph. What do we know about this? I think, have we got everything? Yeah, we know that the root itself is in between minus 0.9 and minus 0.8. Don't know the actual root, but we can try and put that in a second. At this point, we don't want to try and find that really. And we know it's other one from here. We know it crosses at 3 as well. So I'm going to put that in there. So we've got 3. Basically, it comes down here. It's got a turning point at 1.74. Let's just move this across so you can see. At 1.74 and minus 45.37. So that's quite far down here. If that's 3, it's probably just over halfway, somewhere around there. But we know it crosses here, so it kind of comes down through here and then back up, where this point here is 1.74 minus 45.37. This point here is minus 18 from the original curve. And then this is like minus 0.9. This bit here is minus 0.8. Don't know that exact root, so I've just kind of gone somewhere in there. And then lastly, we know this point here is 3. So we've got kind of an idea of what that looks like. And lastly, I just need to label my axes. But happy enough with that. Obviously, we've got the origin, but that's pretty obvious. So, and that's that particular question. So that's locating roots. On to iterative methods now. You can see this is question 9 again from the book. Show that the equation g of x equals 0 can be written as x equals blah. So that's basically saying set this equal to 0. So that's part A. I'm going to do that over the left-hand side. So part A, e to the x minus 1 plus 2x minus 15, where does that equal 0? So I'm going to shift everything over to the right-hand side apart from the e. So e to the x minus 1 is equal to 15 minus 2x, and that looks promising because it's what's inside the ln. I'm going to take out the e itself or unwind that by doing the ln of each side. So I get x minus 1 is equal to ln 15 minus 2x, and then you can see I'm just going to add 1 to both sides. So x equals this ln 15 minus 2x and then plus 1. And that's that. The root of g of x is equal to alpha, or g of x equals 0, sorry, is alpha, using what we've just found, the iterative formula, with x naught equals 3. What's it saying? Oh yeah, it's telling us that we're going to use that. Calculate the values x1, x2, x3. So the first thing we want to do is try and set up our calculator in just a second. I'm just going to write x naught down. So for part B, x naught equals 3. And I'm just going to put x1, x2, x3. So I'm going to put 3 in first and press equals. That saves it on my calculator in its memory. And then I'm just going to put learn. And then wherever I see an xdn or an xn, I'm just going to put ans. So I've got learn bracket 15 minus 2 ans, close bracket, and then plus 1. So this is going to substitute 3 in first. So I get 3.1972 dot dot dot. It does say to 4dp here, so that's not too bad. 3.1524 dot dot dot, and finally 3.1604 technically. I'll put dot 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 there. You can see here it goes 3 to 90, like 3 up to 0.19. That's the difference of 0.1972, and then the difference between this and the next one decreases, and then again it decreases. So every single time, even though it's bouncing up and down here, we are getting closer and closer and closer to the actual answer. This looks to me like it's a cobweb from those values, but it doesn't really matter where we're at as long as we're getting close to that kind of value. And it says by choosing a suitable interval, show that alpha is 3.16 to 2dp. So for part C, because you know that you want alpha to be 3.16 to 2dp, let's take the upper and lower bound of that as our interval. So we're going to take g of 3.155, so the lower bound, and g of 3.165. So this is the lower and upper bound of this. If there's a sign change here, then alpha must be within there and it will round. So I'm just looking at this interval here to try and make that correct. So I'm first going to put in 3.155, go back to my actual thing. So 3.16 bar. Hang fire. I don't want to put it into here. Sorry. I want to put it into here. So it's just, I've not coded my right formula there. So E to the ans minus 1 plus 2 ans minus 15. Right, and now I need to get my actual value. So 3.155, I should have put this in first. Put it in there, so I get minus 0.062. And then 3.165. 3.165, and then sticking that in, we get 0.0446. And again, there's a sign change, which implies that alpha must be between 3.155 and 3.165, which implies that alpha must be equal to 3.16 to 2dp. That is our iterative methods. Okay, next up we've got Newton-Raphson. I will just put the formula up in just a second. Okay, so the formula for the Newton-Raphson method is that xn plus 1 is equal to xn minus the value of your function at xn divided by the value of the gradient at xn. Let's just put that down there. We'll use that in just a second. And that's going to, as mentioned, that's going to locate the root of this just by using tangents here. So that's kind of what we're looking at. So let's just have a quick read through this question. It's y equals f of x, which is x squared sine x minus 2x plus 1. So already looks pretty interesting if we need to differentiate that. I don't think we are actually asked that. Points P, Q, and R are roots of the equation. A and B are stationary points, and they've got x coordinates, little a, little b. So show that curve has a root in each of these. So for this, this is just tedious. It's only worth 1 mark for each one. So the first thing, I'm going to put this lower bound in. If there's a root in each of these, there should be a sign change. I'm going to put 0.6 equals, and then I'm simply just going to code for this. So I've got ans squared, sine ans, and then minus 2 ans plus 1. Yeah. So, and then all I'm going to do is press equals. And I'm going to keep doing this over and over and over again. So this is going to be a little bit boring. So for part A, I'm just going to write all these out. For part 1, I'm going to do f of 0.6, f of 0.7, and show there's a sign change. Part 2, same idea. F of 1.2, f of 1.3. And then lastly for part 3, I'll do f of 2.4 and f of 2.5. So it's just a little bit boring, is this? So I've got 0.0032 dot dot dot. Putting 0.7 in. Is minus 0.8, so there's a sign change. And again, you want to make that clear. So minus 0.08. So this is greater than 0, this is less than 0, which implies a root. You need to be clear with that. I'm just going to write that once right at the end. 1.2, just so boring, is negative. And 1.3 is surely positive. 2.4 and finally 2.5. Worse when it's negatives because you can't do this quite as quickly. Because when you put a negative in, it tries to take it away from the previous answer. There we go. So in each sign change, so there is a root. So sign change in each, which implies there must be a root. Technically, we're told there's only 3 roots, so there must be 1 root in each if we want to get really kind of technical. B, explain why x0 is not suitable to use a first approximation when using the Newton-Raphson. Well, remember little a is a stationary point, so no matter what this looks like, if you're trying to use the Newton-Raphson method, which, just to recall, it basically takes a point and it tries to get close to the root just simply by drawing a tangent at that point, and where it crosses it then kind of jumps back up. So you can see here, this tangent here would go this way, which, apologies, just got a cough. This would now take me back over here. It's really kind of horrible, is this one, because I'm kind of jumping around all over the shop. Then it'd take me over here and find, like, it's going to take me back again. So this one's jumping me all over the place. So it's not a very good one. At least it's doing something though. If you took a stationary point and drew a tangent, well, it's not going to cross the x-axis. So it's going to fail straight away, unfortunately. So that then becomes a bit of an issue, because f dash of that value is 0 and you can't divide by 0. So there's a problem there. So keep that in mind when it comes to that formula. Sorry. So part B, I'm not going to write that out, but there's a stationary point, so you can't divide by 0. So it can't be used as that approximation, actually. Let's just do f dash of a equals 0, and I'll put in brackets stationary point. And can't divide by 0. That'll do for us. Part C, use 2.4 as our first approximation and apply it to obtain a second approximation. Give your answer to 3dp. Oh, wow. So we are going to have to technically differentiate this. If you want a really easy, I don't think I should. Should I show you? Yeah, we should still do it. Technically, there's nothing here that says I can't just use my calculator. So I will do that in a second, because obviously you can differentiate in your calculator. But for part C, we're going to do it properly first. So the first thing we want to do is find out what f dash of x actually is. This is a product rule as part of this. I'm going to write x squared down, differentiate sine x, which is cos, plus write sine x down and differentiate x squared, which is 2x. Just represent that by that, minus 2. So that's the differential of this. We're then going to put 2.4 into that as part of my actual sum. So to get x1, wait, does it want a second approximation? Yeah, it only wants to do this once because that's the first approximation. Phew. So x0 is the first, x1 is going to be the second approximation. So I'm just going to come to one side here. So x1 equals, firstly it's x0, 2.4 minus f of 2.4 divided by f dash of 2.4. So I'm just going to put that in on my calculator using ANS as 2.4. So I'm going to replace 2.4 in each of these equations. So I've got ANS minus, and then on top I've got f of x, which is ANS squared sine ANS minus 2 ANS plus 1. And on the bottom, I've got ANS squared cos ANS plus 2 ANS times sine ANS, and then minus 2. And pressing equals, that gives me 2.430 blah. So that's how you should do it properly, just by putting those values in. But please keep in mind, if I just put 2.4 in here, I can then just put in on my calculator rather than actually having to differentiate this. I've got ANS minus, and then on top, I can code this with ANS again, just like I've just done. So ANS sine x, sine ANS minus 2 ANS plus 1. That's the first bit. Let's just go back and close that. Get rid of that. There we go. And on the bottom, you've actually got the differential. So if I put this in, and my x is actually equal to the ANS, so I want to differentiate. And here I'm going to put x to the 4th. This is the actual, sorry, x squared. This is the actual f of x itself, but I need to code for this as I normally would. So x squared sine x, close bracket, minus 2x plus 1. And I want to find out when is that equal to 2.4. So I'm just putting that in. Press equals, and it also tells me 2.4301. Doing it this way means I don't actually need to differentiate anything, and I still get that second approximation. I do think for 4 points, though, it's expected that you're going to differentiate that using that product rule just to show off those skills. So that's the Newton-Raphson method. Finally, we've got how kind of we can apply these things to basically just different methods, I suppose, to modeling questions. So here we've got Ed throws a ball for his dog. The vertical height of the ball is modeled by this horrendous function. So I'm probably going to have to do some of this and skip around a little bit. So, but why is ht shown in this diagram? So we know it goes up and it comes down. Show that the t quantity of a is the solution to, and then it's got t equals blah, blah, blah. So t quantity of a. So that is when y equals 0, isn't it? So to get that, we know it's when y equals 0, when h of t equals 0. So I'm going to set that, basically, that equation equal to 0 and start seeing what in the world's going to happen. So part A, I know it's going to be that 40 sine t over 10. Now remember, we're trying to solve this. We're just trying to get it into this kind of rearrangement. 9 cos t over 10 minus 0.5 t squared plus 9, and that's equal to 0. Now the first thing I'm seeing here is every coefficient in this has been doubled. So I imagine that's because this gets doubled. So I'm just going to times everything by 2. I'm just going to update that on here. So that one's going to double, that one will double, and this will double. And so this one. So I'll just put all those in now. There's a minus t squared plus 18. This cos will become an 18, and this sine will become an 80. So that's just because I'm linking it up with what's in there. Next up, I'm going to take my t squareds across to this side. I think, actually, let's just double check. Yeah, I want the 18. Yeah, I'm just going to take t squared across from here and then just square root. So I get t squared equals 80 sine. I'm not going to keep writing this out, so I'm going to do it once and then I'm going to add the square root sign in. Minus 18 cos t over 10 plus 18. And then, of course, to get my answer, I just want to square root that. So getting rid of the square root, I'll get that thing going on. Now we know t is time, so it needs to be bigger than or equal to 0. So I'm not going to put the plus minus in front of this. In the question, I told it's the positive. To find an approximation for the t coordinate of A, we've got this iterative version or this iterative formula that's being used. So let t naught equal 8 and then find the values. So we'll just do B up here and we'll put t naught equals 8. And we've got to find t1, t2, 3, and 4. Actually quite a few. Remember, all you're going to do is on your calculator, you're just going to press equals eventually. So we're starting with 8. And then I'm just going to code my calculator for this. So the square root of 18 plus 80 sine. And then here is where it comes in. So we've got ans over 10. And then minus 18 cos, and then ans over 10. I think that should be all. And press equals. You have to keep writing these down. Obviously, you don't have to jump between. You're just going to press equals and then write these down. Technically, I should round these properly. I'm just going to write a dot, dot, dot. You can kind of see where these are going for each one now. And then finally, oh, too far. And that's it. So these should have been rounded. I think this second and fourth one would have been rounded slightly differently. But you can see the actual thing that's going on there. Part C is find H dash. So you're actually going to have to differentiate that. Which is a bit of a pain. There's no cheating that. You can't just stick it in your calculator. They're pretty much forcing you to do this. So we're basically going to differentiate this thing. We know that this bit here will kind of stick. This 9 will disappear. Sine goes to cos, cos goes to minus sine. So we can kind of pull bits out. But when you differentiate, remember you're going to times by the differential of the argument of the function. So each of these can get times by 1/10. So this 40 is going to become 4 cos, and then it's going to be t over 10. Minus 9 will become 0.9 or 9/10. And then the minus cos is going to become a positive sign. And that'll be a t over 10. Minus a half t squared will just become minus t. And then the plus 9 will disappear. So that is our differential. And then part D is taking 8 as the first approximation, apply that Newton-Raphson to obtain a second approximation, okay? So part D is we're just going to basically, we've got x1 is 8 or x0 in this case. x1 is going to be equal to x0 minus f of x0 over f dash of x0. So that's just writing it out properly. And we're just going to stick this in using these formulas. For us, you can cheat this like I did in that last one, or you can go through properly. You could find these values out individually and put them all in. I've been using f here. Technically, we should change that to be an h. So I'll just put h and h. Okay, and from here, let's just put those in. So 8 equals, we're going to do ans minus, and I'm going to do this using the cheat. So 40 sine ans over 10. It's 9 cos ans over 10. Minus 0.5 ans squared plus 9. And then at the bottom, I'm going to use the differential function and just put that exact same thing in again, but at the ans. So 4. And then instead of ans this time, we're going to use x because it needs to be x over 10. And so I'm using x here instead of t, just because it's all this calculator can do. It's the same idea. So just going through bit by bit. Plus 9. And remember, I want to do this at x equals ans. So I get 7.8738. So x1 equals 7.873. Let's go 9. Let's round that properly. Hence suggests an improvement to the range of validity of the model. So what have we got here? The range of validity. Let's have a look at that. Let's just move my calculator out of the way. Look at this graph. So now we've got a nice approximation for A. The range of validity, well, it can't be negative. We know it's going to be bigger than 0, but obviously it can't go negative again after A, because this parabola is going to keep going down potentially, or this curve, and then it might turn back up and cross again. So I think this, well, we know this question is basically saying, let's restrict it to just be from here to here, just so we get that first part of this curve when it goes up and down. So the final little bit here for E is going to be restrict the model to, and then we want T to be between 0 and up to A itself, whatever that actually is. In our case, we've got an approximation for it, but we know it's between those two, and that's that. So that's applications to modeling. Hopefully these 4 questions will hopefully help a little bit, get some understanding. If you've got any more, just either ask me, well, yeah, just ask me at some point, shoot me a comment, and I'll get back to you shortly.